In section U2A1, it's just a review of grade 11 physics as far as forces go, and I'm just going to go over a few points that I need you to remember from grade 11. So a force is any push or pull. Some of the forces that we're going to be dealing with, and we're just going to hit the major ones because we can split these up into smaller categories if we want. We've got the force of gravity, which is going to equal mass times acceleration. Remember, the Earth exerts a gravitational pull on another object of negative 9.8 meters per second square. Anything that has mass does exert a force of gravity. So the Earth is just one example. For example, the Moon has 1/6 the force of gravity that Earth does. Remember that gravity is proportional to the mass of the Earth and also the distance you are away from the Earth. Now that's a formula we're going to look at later on in this course. Remember, what we're doing is Newtonian physics here, so we're looking at relationships, mathematical relationships. Einstein attempted to describe why gravity occurs, and so he talks about the space-time fabric, which also is dealt with later on in this course. The next one I'm going to go to is an applied force. So an applied force is like a push or a pull. When we actually have our hands on something and we push it, we have an applied force. If we hit a ball with a baseball bat, we have an applied force. Now, the opposite of force of gravity is normal force. Remember, forces act in pairs, always. So if we had a box on a desk and it was being pulled down by the force of gravity, then the normal force is acting in the opposite direction to that. So if gravity is 980 newtons, the normal force would be equal and opposite. It would be also that 980 newtons. Force of friction. We could also put air resistance into this. So force of friction is going to work opposite to the applied force. And we'll get to that in a minute. And the last one is the force of tension. So if something is being held onto by a rope and it's hanging, we have a force of tension in that direction. So an applied force is when something from the outside of the system is exerting a force on it. So for example, pushing this block right here. Now remember, the force of friction will act in the opposite direction. Just a reminder, if you hit a baseball, there is only an applied force while the bat is in contact with the ball. At this point, there is no force on that ball. There is a force of gravity acting on that ball right now, and there is a force of friction from air resistance happening on that ball. But as soon as the ball leaves the bat, there is no applied force on that ball. Just a reminder of some things with normal force. Once again, if you put your hand on a desk, you can feel the pressure from the desk pushing back on your hand. Push down harder with your hand on the desk, and it'll feel like the desk is pushing back harder. So the normal force is going to go against whatever surface you're on. Some people think that the normal force is always going up, but if you put a book against a wall and you put an applied force onto that book, then, oops, I'll draw that arrow over there. If you put an applied force or you push that book in towards the wall, the normal force will come out perpendicular to that surface. Folks, there are different ways of drawing free body diagrams. Use whatever method you used last year, and I'll be fine with that. The only thing that you might have now, which will be different from last year, is a question on a ramp. So let's do one ramp question. It might serve to be a good reminder of some of the work that you did last year if you did do this. Let's say that we have a 10 kilogram brick, and let's say that there's an applied force of 50 newtons on this brick. Now, let's say that the force of gravity is coming down. Let's call this angle on the ramp 30 degrees. So the force of gravity here would be mass times gravity, and that would equal to 98 newtons, if that's 10 kilograms, because it would be the mass of 10 kilograms times 9.8 meters per second squared. The problem here is, well, we've got a couple of problems. The normal force goes perpendicular. The normal force goes perpendicular to the ramp. So it's not going in the same direction. So what we have to do is we have to take this angle here, and to get our force normal when we're on a ramp, it's cos 30 times the 98 newtons. Because this is on an angle to this, we must put the cos of whatever the angle of the ramp is, and we must times it by the force that's being exerted by gravity. I highly suggest, if you haven't seen things on ramps before, that you watch a couple of videos of the physics of forces on ramps. Now here's another one. Gravity's not pulling the brick straight down. The brick can't go through the ramp. Gravity is pulling this brick down on an angle. So if we draw the normal force straight through the brick, or the line from the normal force, and then we make a triangle here, to get the force of gravity that's in the x-plane or going down the ramp, it's going to be sine of 30 degrees times that 98 newtons. So I took the 30 degrees from there. It's sine 30 times the 98. So what you have to realize here, and just give me 1 second, and I'm going to do the calculation of that. We have sine of 30 equals times 98 should be about 47.5. Uh, 49, sorry about that, folks. So we have 49 newtons in this direction. So let's say we don't have any friction on here. Our net force is going to be the force applied minus the force due to gravity in the x direction. So we said that we put 50 newtons of force pushing that up the ramp, and we've got to subtract the 49 newtons that is due to gravity. So this brick's being pulled down the ramp this way. So if you want to know the force of gravity on a ramp, you have to take the sine of the angle of the ramp and multiply it by the gravitational pull, which is mass times gravity. If you want to know the normal force, you take the cos of this angle and times it by the force of gravity. Now, let's say that we had a force of friction of 0.5 newtons. We would also subtract that, and we would end up with 0.5 newtons of applied force going up the ramp. Once again, if you have not worked with forces on ramps, or you're a little shaky on what's happening, I only went into a little bit of detail here. Try to watch a Khan Academy video of free body diagrams and forces on ramps.